Today we're going to be talking about increasing and decreasing functions. So the formal definition of increasing and decreasing is if you have two x values where x1 is less than x2, function is increasing if the y from the x that's less is less than the y that's for the x that is greater. Or I'm decreasing as I go from a smaller x to a bigger x, that my y's are getting bigger. Now in terms of the derivative, because we're in calculus, and now the derivative matters. If your derivative is positive, then we are increasing over an interval. If your derivative is negative, then we are decreasing over an interval. Two other key terms that we need are a critical point, which is when your derivative equals 0 or your derivative doesn't exist. And you want to make sure you have these definitions in your notes. So again, a critical point is when your derivative equals 0 or your derivative doesn't exist. And then we have a stationary point only when the derivative equals 0. Now really the difference between these, stationary. When you are stationary, you're not moving. So think about it that way. Your derivative equals 0 at a stationary point, but your derivative can also be undefined for critical points, and those are going to be very important to us as we work through this chapter. Okay, using analytic methods, find our local extrema, and then intervals of increasing, decreasing. So we find your first derivative. That's your first step. And you set that derivative equal to 0, and you figure out where the derivative is undefined. Now this derivative is never undefined, so we don't have to worry about that. All we have to worry about is when the derivative equals 0. So we have some points in here, and this is where all that algebra that you guys are so good at comes into play. Okay, so that is at 0 and positive and negative 2. Now to help us organize our work, do a number line chart where we're looking at the sign of the derivative. And I label my number line chart so I know what I'm looking at the sign of with all of our points, with negative 2, with 0, and with a positive 2. Now you're figuring out the sign, whether your derivative is positive or negative. So pick a number less than negative 2, plug in negative 3 in each one of these factors and figure out whether you're positive or negative. Honestly, it doesn't even matter the value. So what you want to look at, if I plug in a negative for that first one, I'd have a negative. If I plug in negative 3, I would have another negative. And then I would have times by another negative. So I'd have a negative times a negative, which is a positive, times by a negative. So I'm negative, which means our function is decreasing. Plug in negative 1. I would have a negative times by another negative times by a positive. So this is positive. So I'm increasing. Between 0 and 2, plug in 1. That would give me a positive, negative, positive. So we're negative on that interval, so that means we are decreasing. And then plug in a number greater. For each one of those, we are positive. So that means we are increasing. So this is not just your work. You have to write it out. So we need to say f of x is increasing on our interval from negative 2 to 0 and from 2 to infinity. Now check and see what the book does. I think this is when the book and I disagree. They might have these be inclusive of negative 2 and 0 and positive 2. So when you're going through the book, just check and see what they're doing. And same thing with my math lab. I think those might be inclusive. F of x is decreasing, and we're decreasing from negative infinity to negative 2 and from 0 to 2. And you know what? Let's put a little reason in here. Because f prime of x is less than 0. And I should have in here because f prime of x is greater than 0. Okay, so give me a little reason. Now we need to find the local extrema. So let's look at this. I have a decreasing function. Then I change to increasing. Then I go back to decreasing. Then I go back to increasing. So we're going to have some local max and mins, or relative max and mins. Here is going to be a relative min. So a local or a relative min at -2. And then when you plug in -2 in for x, you get a 0. I would also have a relative min at a +2. So when I plug in 2, I'm plugging 2 back into the original function because I want to know that point. And then our local or relative max is going to happen when I went from increasing to decreasing. So that's at 0. When I plug in 0, we get 16 out. Okay, our next example. Again, doing the same thing. But as we increase, our derivatives and our functions are going to be a little bit more challenging. So I find my derivative. So derivative of the first, leave the second alone, plus leaving the first alone, derivative of the second, set that derivative equal to 0, and factor out anything you can. So we end up with a 1 plus a 2x squared. So I have when e to the x squared equals 0, and I have when 1 plus 2x squared equals 0. E to the something is never going to equal 0. So this is going to be a never, so I never equal 0. I have no critical points. Here I have an x squared equals a -1/2. That is also a never. Also here, our derivative is never undefined. So we need to figure out whether I'm either always increasing or always decreasing because I never equal 0. So therefore, if I were to plug in numbers into my derivative, if I plug numbers in here, e to the some power is always going to be positive. 1 plus 2 times something squared, that's always going to be positive. So I have a positive, another positive, so f of x is always increasing because f prime of x is always greater than 0. So therefore, f of x has no max or min. Because I'm always increasing. Okay, our next example. So here we find, again, our derivative. So low d high minus high d low. Draw a line, square the below. So simplifying that, so now we need to look and see where is our function undefined and where is the function equal 0. So a function equals 0, especially when it's a fraction, when the top equals 0. So that's when x squared is equal to 2. So that's when x equals plus or minus root 2. And then you have to look, a fraction would be undefined when the bottom equals 0. The bottom's never going to equal 0, so we don't have to worry about that. So our only critical points are positive and -2. Okay, so we have a negative root 2 and a positive root 2 that I'm testing on my first derivative. So when I plug in a number So say I plug in -2 into my derivative, which is down here, the bottom's always positive. So really we're just worried about the sign of the top. So if I plug in 2, we would have a negative. So therefore I'm decreasing on that interval. When I plug in 0, you always want to try and plug in 0. When I plug in 0, we're going to get a positive on top, positive on the bottom. So that means I'm increasing. When I plug in +2, again, we're decreasing. Okay, so we are decreasing. F of x is decreasing on our interval from -∞ to -√2 and from √2 to infinity because f prime of x was less than 0. F of x is increasing on our interval from -√2 to √2 because f prime of x was greater than 0. Now again, let's look. Okay, our function was decreasing, then I changed to increasing, then I changed back to decreasing. So when I went decreasing, decreasing, changing to increasing, that's going to be a relative min. So I have a relative min at -√2 when I plug that back into the original. Okay, so I'm plugging that back into the original. We get a -√2 over 4 out of that. And then we have a relative max. Okay, when I go from increasing to decreasing at a √2, and again plugging √2 back into your original, we have a √2, also over a 4. Just this is the positive version. That's it for today. Please make sure your lesson summary is submitted on time.